Pre-calculus students, welcome to your 9.3 notes. Today we're going to talk about hyperbolas. It's the final three of the conic sections. When I say three, I mean four, because of course you know circles count different from ellipse. So we got circles, we got ellipse, we got parabolas, and now hyperbolas. Hey, so we're going to look, first of all, the definition of a hyperbola is the set of all points in a plane where the difference of whose distances from two distinct fixed points, called the foci, is a positive constant. I find that definition a little bit difficult to grasp at times, but what we're talking about when you see these D1 and D2 values, the difference between them is constant. Again, kind of hard to grasp that, but we're going to show you some ways to graph without having to worry too much about that particular definition. Now, if you look at the next diagram, you'll see we've got several things labeled. We've got an A value, we've got a B value, we've got a center, vertices. The transverse axis is important. That's the axis that connects the foci together. And then each side of the hyperbola is called a branch. All that stuff will come into play. It is important to consider there is a B value on here as well that we will use. You just don't see it on this particular diagram. The other thing that's kind of next to that is the asymptotes of a hyperbola. I'm going to suggest to you that you don't need to spend a lot of time memorizing that formula. If you follow the graphing techniques that I use today, you'll be able to figure out the equations of the asymptotes without having to memorize anything. Just simply look at it and you'll see the equation for those lines. We're going to use your old friend point slope on that one. Okay, so again, lots of little details. We'll work through those as we move ahead. Now, as we scroll down here, you can see we have standard forms. We have a horizontal standard form and a vertical standard form. When you analyze those, you quickly realize some similarities, like they're both subtraction. Both of them have a squared first and then b squared to follow. But here's the big difference. The horizontals, like the two that we have up above, have an x minus y situation, where the vertical have y minus x. I should probably point out here too that A isn't always bigger than B. It can be smaller, it can be bigger, it can even be the same as B. But it's different from ellipses in that A was always the biggest in an ellipse. That is not the case with hyperbolas. C is always going to be the largest of the three. Okay, and so I'm again highlighting the fact that it's a subtraction situation. Hey, one other thing you notice on the right, you see how it says c squared equals a squared plus b squared? That is the relationship between sides A, B, and C. It's the relationship you have grown to love and to know, the Pythagorean theorem. It's none of that silliness that we saw on the ellipses. So again, you need to recognize these forms, know which is horizontal, which is vertical. But when we get through the graphing side of this, some of the techniques we use will help you to keep that information straight. Okay, so on number one, we need to find the center, the vertices, the foci, and the asymptote equations for the hyperbola, and then we'll sketch the graph. So the first thing I notice, in a similar fashion to what we had on ellipses, we can pick out the center very quickly. We can see that there's no movement from the origin, so it's still at the origin. Also pretty quick to pick out would be the A and B values. Remember, A is always first, so a squared is 9. That means A is 3. B would be 4. And then we know the relationship is the whole Pythagorean situation. A squared plus B squared equals C squared. That's your nice, simple Pythagorean triple. So C is 5. Okay, at this point, what I typically do is start marking down some of the key stuff. So I've marked the center of this graph to be right on the origin, and then I'm looking at the A value, and I see that the A value is 3, and I also see it's connected to X. When I see it's connected to X, that reminds me it's going to be horizontal, so I need to mark a point 3 right and 3 left. By the same token, I see that the B value of 4 is connected to the vertical variable y, so therefore I'm going to mark a point up 4 and down 4 from my center. Now here's something we do is a little goofy, but it really helps us with our sketches. We draw a rectangle. Again, this rectangle is not actually part of the graph, it's just a guide. That's why I'm drawing it dashed and why you should do the same thing. But it's very, very helpful. It tells us a few things. One, it kind of helps us to see where the vertices are. If and I'm marking the vertices in red now, but the vertices, I know that they're on the left and right because this thing is x minus y. It has to be horizontal. Here's another thing. If you draw the diagonals of these rectangles and extend them, both directions, these are the asymptotes for the graph. Okay, so this is pretty cool stuff. You've got your asymptotes, you've got your vertices, and so honestly at this point all you really have to do is start at the vertex on either side and draw either side of your hyperbola like you see I'm doing here. And there it is. There's the hyperbola. Now there's one thing I haven't marked just yet. The foci, we'll put those on there as well. So I see that the foci come from the C value. The C value is 5, and they're always going to be the same direction. So since this hyperbola opens horizontally, I know the focus points are inside the hyperbola, 5 units from the center. Okay, we let's mark it all down. The vertices, we went 3 spaces left and right from the center, so we can just write those as plus or minus 3 and 0. The foci, we did similar thing where we started at the center, but then we went left and right 5 spaces, and we can mark those plus or minus 5 and 0. Okay, the last thing we're going to look at is the equation for the asymptotes. Now you can see there are these just 2 lines, but here's what's great about these 2 lines. The slopes are opposites from each other. So, and they share that point, that center point. So we can use our old friend point slope, and we can just write y minus 0 equals, and then we find the slope, and if I look over there I can count. It's 4 and 3, 4/3, or the other line's negative 4/3, and then times x minus 0, or just simply plus or minus 4/3 x. And we're done. Let's do another one. Very similar question in some ways. This one will be vertical. I can see that right away because it's y minus x, but the center is still at the origin. Once you kind of get that, then we'd want to go ahead and find those a and b values. This time they're 5 and 1. By using that Pythagorean relationship, we know c would have to be the square root of 5 squared plus 1 squared, or just simply square root of 26. Once you get here, it's really not too big of a deal to go ahead and draw your center and then start sketching your box, or your rectangle I should probably say. Now this rectangle is a little funny because it's so narrow and tall, so a little different than some of the others, but that's fine. It works the same way. So again, go ahead and use the dash lines and draw the box, the rectangle that connects those 4 points, and then we use the diagonals from that rectangle allow us to have the asymptotes for our graph. I'm just getting those extended in all 4 directions here. Now again, remember this particular hyperbola is vertical, so I know that this hyperbola is going to open up and down, so I'm going to sketch using the vertices on the y-axis. Basically, it's going down and going up. Like you see here. All right, We still haven't mentioned the foci, but we found the c value was square root of 26. If you think about square root of 26, it's just a smidge more than 5. We're not going to worry too much about precision here. It's going to be real tough to be able to tell the difference between square root of 26 and 5.5 or something like that. So we're just going to approximate it. We will label it down below though. So first of all, here are the vertices. We know those are going to be up and down 5 spaces from the center. So we'll just do 0 plus or minus 5. And the foci are up and down square root of 26 spaces from the center. So 0 plus or minus square root of 26. Last thing we need to do here is we need to go ahead and write the equation for the asymptotes. We're going to follow the same format. Y minus 0 equals. Now we'll find the slope. In this case, the slope of those lines is either 5 or negative 5. So we'll do plus or minus 5. And again, it's x minus 0. So we can just do plus or minus 5x in this case. And there it is, a vertical hyperbola. Pretty cool stuff. And now for number 3, you might notice right away on this one that we have a couple of little things to deal with that we haven't had to deal with yet. One of those being that the center has now moved away from the origin. Finally, center is -1 and 2. All right, no big deal there. Here's what you may not love so much, the fractions. So what's going on here is our a value and b value have to be the square root of 1/4, square root of 1/16. I've got those values. And I might as well go ahead and find c while I'm at it. I know I don't have to label the foci immediately, but might as well go ahead and get them. All right, so here we go. This is 1/4, this is 1/16. Add those together, you get 5/16. So c would be the square root of 5 divided by 4. Now, I have the advantage of kind of looking ahead on this problem, and so I know that I really want to change the scale on this graph. Instead of counting by ones like we typically do, I'm actually going to count every 4 spaces counts as 1. Now you might be able to look at our values and figure out what made me decide to do 4 spaces. The biggest reason would be, well, first of all, we have small numbers for the center, -1 and 2, so I know I didn't have to move too far. But the other issue was the b value being 1/4. If I make every space worth 1/4, that makes it much easier to go ahead and draw that rectangle in the middle. So here we go. Our center is at -1 and 2, which would put me right about there. And let's see, our a value is 1/2. That means I'm going to need to move in the vertical direction half a space up, half a space down. And horizontally, our b value is 1/4, so I'm going to move 1 space each direction. And you might already be thinking about this. We are going to be going off our grid just a little bit with the hyperbola. I still think it's better to go ahead and stretch this thing out a little bit rather than trying to draw some super duper tiny hyperbola that fits, but we can't really do anything accurate with it. So I'm jumping ahead and drawing the asymptotes that we're going to be using here. And need to stretch those the other direction as well, right into the words for the problem. That's all right. And we kind of know as well the direction, since it's y squared minus x squared, it's vertical. So I know the hyperbola is going to look something like this and this. Okay, other things I know. We found that the foci was square root of 5/4 was the c value. So the foci would be just, square root of 5 is just a little more than 2. And so 2 divided by 4 is 1/2. It's a little more than 1/2. I'm not going to worry too much about trying to be precise on these because, again, I'm not sure you're going to be able to tell the difference between 2.27 and 2.35 and 2.5. We're approximating this whole thing. So, all right, we've listed the center. Let's talk vertices. From the center, we would move, of course, up or down a half a space. Those are our vertices. The foci, also moving up or down, but by square root of 5/4. And then our equation for the asymptotes. This is where the whole point slope form thing really can come in handy. And so I'm going to write it like this. I'm going to do y minus 2 equals, now our slope, I know that each of these spaces count for quarters, not for ones, but truthfully our slope is still up to, right, 1. Our slope is 2. So it's plus or minus 2 times the quantity x plus 1. Now, some teachers might prefer that you go ahead and move that 2 to the other side and make it 2 plus or minus 2 times x plus 1, something like that. For me personally, I'm okay with either of those forms, but talk to your teacher to make sure they aren't picky about something like that. All right, and I think we've covered that one. Let's continue on. All right, we've got one more graphing problem before we get to our clue problems, and you can see the situation here. We've run into this with other figures, so this doesn't really bother us anymore, but we're going to have to do a little completing the square. All right, so here's what I'm going to do. I'm going to do x squared, and I'm going to factor a 9, and you got to be careful. It's really a negative 9 out of those two. So y squared minus 4y. I'm going to leave myself a little space, and I'm going to say equals 72. Now we know when we complete the square, we do half of b, and we square it. Now you might be tempted to put plus 4 right there, right? But this isn't really plus 4. It looks like it's plus 4, but it's negative 9 times 4. So this is actually minus 36. All right, there we go. So let's go ahead and clean this up. X squared minus 9 times y minus 2 quantity squared equals 36. Now what I need to do to get this into the standard form is to divide both sides by 36, and that sets it equal to 1. So x squared over 36 minus y minus 2 quantity squared over 4 equals 1. All right, let's start picking out some of the key information here. The center, that would be at 0 and 2. By the way, we also know it's going to be horizontal. A is going to be 6, B is going to be 2, 6 squared plus 2 squared, square root of 40. So C is the square root of 40. If you want to change that to 2 square root of 10, that's fine. That's probably, better. But I don't know. I'd rather approximate square root of 40 if it's me. So I'm going to leave it like that. So there it is. There's the center at 0, 2. Again, we know A is connected with X, so that tells me to go left and right 6 spaces from the center. I need to go up and down 2 spaces. And then we can draw a rectangle. I've always found that if you really understand the other conics that lead up to hyperbolas, these aren't that bad. These can look a little intimidating for the rookie, but fortunately, you guys are seasoned veterans, so it's not really a problem for you, right? All right. So again, I'm just extending the diagonals of the rectangle, and I have to keep reminding myself, which direction does this go? Which direction does this go? Because it would be simple to mark it the wrong way. If you just look at it, you really cannot tell. The way I can tell is in the standard form. It's x squared minus y squared. That thing is horizontal. It's going to be like this and like this. Okay. Quickly, the last couple things we need to do, we need to mark those foci on there. Square root of 40, it's a little over 6. I'm just going to go 6.5, and I knew that was 6 spaces out, so I'm really truly just roughly sketching where those would be, but I can label the exact points over here. So the vertices we know would be exactly, well, we go how far from 0 to? We go left and right 6 spaces, so we're going to do plus or minus 6 comma 2. The foci, we go right from 0 to exactly square root of 40, so it's plus or minus square root of 40. Again, if you want to be fancy with stuff, you can make it 2 square root of 10. That's probably a more preferred answer, but I don't know, I just like approximating non-simplified radicals if I have to choose. All right, and then the last one, the asymptote equations. All right, so it's going to be y minus 2 equals, and I'll go in here and count this slope. It's up 2 and right 6, so it's plus or minus 1/3, and this would be x minus 0, so just 1/3 x. I believe we have answered all the questions. You know, one thing we haven't answered is the eccentricity, and that's something for you to think about. I'll go ahead and put it on here even though it didn't ask for it. But if you remember, eccentricity from the ellipse and from the circle was just c over a. You know what? It's the same thing here. And our c value was square root of 40. And our a value was 6. This ends up being just a hair over 1, which is great, because if it were less than 1, it wouldn't be a hyperbola. All right, up next, we're going to look at some clue problems. Now, my advice to you on a clue problem is, unless you're 100% accurate, do yourself a favor and do a quick sketch and just try to remind yourself what it would look like. Vertices are at plus or minus 4 and 0. The reason I'm doing this is by just simply knowing the vertices, it reminds me which way this hyperbola opens. That's really helpful. Okay, now the center is at the origin, they say, which I could have actually figured that out based on the vertices or the foci. But the other thing I need to know is I need to figure out that b value. I know a is 4, I know c is 6, so 4 squared plus b squared would be 6 squared. So b squared is going to be 20, 36 minus 16, and actually when we think about standard form, I'm going to be all right just to know b squared. So it's x squared over something minus y squared over something. Let's make sure you understand where that's coming from. I know x is first because it's horizontal. I know it's minus because it's a hyperbola, not an ellipse. And the other part I know is the center is at the origin, so these are just x and y squareds. It's always equal to 1. A is always going to be first, and by a I mean a squared, and then b squared is always second, and we have ourselves a lovely equation. All right, here's your next one. The foci this time it says are at 0 plus or minus 5. So again, I think it's smart just to do a quick sketch, just to remind yourself, if the foci are at 0 plus or minus 5, that means this thing has to open around those two foci, so it's essentially opening up and down, it's vertical. Just something to keep in mind. All right, also knowing that the foci are 0 plus or minus 5 tells me that the c value is 5. They gave us the center being at the origin. Now the asymptotes being plus or minus 2 is a little bit interesting on this one, okay? We're going to have to figure out, is this an a over b or a b over a situation? In other words, when I jump ahead here, I know it's going to be x squared or y squared. And in this case, we know it's going to be, actually, I'm going to just write this up here. We know it's going to be y squared over a squared minus x squared over b squared equals 1. We know this because it's vertical, right? So I know my slope has to be a over b. So I know a over b has to equal 2. That's the slope of the asymptotes. So what I'm going to do, and this is a little interesting, but I'm just going to multiply both sides by b, so I'm going to know a equals 2b. And when I do my Pythagorean, it's going to be a squared, but we know a is 2b, or not 2b. That's, never mind. I can't resist that. Yeah, sorry. Dad jokes win the day. All right, so 4b squared plus b squared is equal to 5 squared. So this is going to be 5b squared equals 25. B squared is going to equal 5. Now, again, we remember that, hey, if you know b squared, that's really all you need for the standard form, but there's an issue here. We also have to figure out a. So I'm going to do this. B is equal to the square root of 5. That tells me that a is 2 times the square root of 5. All right, and perhaps more important, a squared, if you square that, that's 4 times 5, so that's square root of 20. Oh, not square root of 20. Apologies, just simply 20 is a squared. All right, that number is going to be important to us because that's the one that we're going to plug in right under our y value. Y squared over 20 minus x squared over 5 equals 1. A little bit going on there. That's a little more challenging when you get the equation for the asymptotes rather than directly an A, B, or C value. All right, let's take a look at number 7 here. This time we're still trying to write the standard form of the hyperbola. We're given vertices and a point that it passes through. Well, first thing I want to do is I'm going to use the vertices to find key information like the center. We could also, because the distance between them is 4, we can find that the A value is 2. And we should also probably remember that you can also tell if it's vertical or horizontal based on the position of vertices, and in this case they would be horizontal. And I'm going to go ahead and sketch just a rough graph. Again, this isn't going to be precise, not even close to precise, as you can tell, but I'm just sketching the general shape, not so much to pick specific points or anything like that, but just simply to see it and remind myself this thing is absolutely horizontal. All right, we've got the center, we've got the A value, we've got that it's horizontal. If we plug everything we know into the general form, or the standard form equation, we'll be able to find out what do we know, and B, what's left to figure out. So we know it's horizontal, so we know it's going to be x squared over a squared. We know a was 2, so we can just change that to a 4. Then it's going to be minus, again, hyperbola, minus, and it's y minus 1 squared. We don't know b, so we're just going to write that as b squared for now. We'll come back to that, but we know it equals 1. So what I have now is one equation, and I have 3 unknowns, x, y, and b. But fortunately, this problem gave us a point, 5 and 4. So we can actually take that point, 5, 4, and plug it in for x and for y and see what we come up with. So 5 squared is 25. 4 minus 1 is 3. Square it, you get 9. It's equal to 1. All right, not the prettiest equation to solve, but one we can do. If we subtract 25 fourths from each side, we'd get negative 9 over b squared equals negative 21 fourths. There are a lot of ways to solve from here. Probably the way I would advise is using the cross products property. Some of you call it cross multiplication. Negative 21b squared equals negative 36. And finally, b squared is equal to 36 over 21. Now, remember, we're writing a standard form equation, so we technically don't need b, we just need b squared. All right, so I know A, I know B, I know the center. I truly at this point have everything I need. Oh yeah, we should go ahead and simplify anytime we have a fraction like 36 over 21. Let's change it to 12 sevenths, and then we'll plug it in for b squared. Okay, it's a little weird that we're going to have a fraction over a fraction, so I'm going to show you 2 versions of the answer. The first one isn't necessarily wrong, but it's not great mathematical notation. We don't like it when we have complex fractions, or compound fractions is probably the better word choice there. And so what we can do, we know when you have division by something like 12 sevenths, that's the same as multiplying by 7 twelfths. So I'm going to rewrite this as x squared over 4 minus 7 times y minus 1 quantity squared over 12 equals 1. This is exactly the same as doing, dividing by 12 sevenths. I know that seems a little strange to do that step, but you can handle it, and some teachers are pickier than others on that. Okay, so for number 8, this one I think is a lot simpler. We see we have vertices at 3, 6, and 3, 0. That allows us to find pretty simply the center has to be 3 and 3. We also, based on vertices alone, could figure out that our A value would be 3. We can figure out that this thing is going to be vertical, right? 3, 6 and 3, 0, one's above the other. And I'll do a little sketch. Again, some of you can probably get away without doing this, but I really encourage you to take the couple minutes that it takes to do the sketch. It's almost always worth it. It's rarely something that would be a waste of time. It only takes a few seconds. All right, so we can see that it's vertical based on the location of vertices. We can kind of confirm that. So now I'm looking at the asymptotes, like, okay, well, what information am I going to get from there? Well, the one thing we can get is the slope. And the slope is, for the first asymptote, it was -1. The second was +1. So we know m is plus or minus 1. That's the slope. That's the slope of the asymptotes. So how does that help us? Well, in this particular case, we know it's going to be a over b because it's vertical, and a over b is the way the slope's going to go. So a over b has to equal 1. We already know that a is 3 and a has to equal b. So if a is 3, b is 3. We just found all that information. And now let's just plug it into standard form. So we're going to have x minus 3 squared, excuse me, y minus 3 squared minus x minus 3 squared. And a and b are both 3, so there are going to be 9s under both of those. All right, here is the last topic for the day. We're going to look at general equations of conics. You can see ax squared plus cy squared plus dx plus ey plus f equals 0. I know b's missing. We'll come back to that another day. It's a rotational item we'll look at later. Essentially, we have these 4 options for the conics. And I would say it's probably not worth your time to go and memorize all these. You'll kind of think through them. If you understand the equation of a circle, parabola, ellipse, hyperbola, these will make sense to you. So the first one says it's a circle if a and c are equal. We've seen that already. If we have a 4x squared and a 4y squared, that's a circle. If we have a negative, we haven't run into this one, I don't believe, but if we had a negative 8y squared and a negative 8x squared, again, circle. Okay? If a and c, if only one of them exists, is the way I think about it. So if there's an x squared term but not a y squared, or vice versa, definitely a parabola. Okay, that's the only way you can have one, not the other, is if it's a parabola. And then for ellipse and hyperbola, if it's not a circle, not a parabola, it's going to be one of those two based on what we're doing here. And I would just look at, are the signs the same? Okay, if the signs are the same, the product is going to be positive. If they're different, it's going to be negative. And if their signs are the same, we're going to have an ellipse. So let's start just finding values for A and for C. So on number 9, we see A is 4. There isn't a y squared term, so C is 0. Boom, done, parabola. That's how fast these are. On number 10, we know our A value is the coefficient before x squared. Our C value is the coefficient before y squared. The signs are opposite. Guaranteed to be a hyperbola. Okay, number 11, you can see we have a 4x squared and a plus 4y squared term. So that means both A and C are equal to 4. Oops, I wrote B. I meant C. I knew what I meant. Just ignore that B. That's a C. I'm not going to change it. But it's a C is equal to 4. So that one's a circle. And then on the last one, number 12, you can see that A would be -7, C would be -1, and they're both negative, but they're different. That has to be an ellipse. Again, this last topic, I think you should probably breeze through it. If you understand the forms, the general forms for these, it should work. There is a lot going on today. Again, thanks for lasting till this point in the notes. There's a lot to absorb today. The nice thing is, you guys are a pretty intelligent group, and I know you can handle it. So hey, you guys have an amazing day, and figure out how to graph these hyperbolas, all right?